So my name is Madison Dixon. I'm the Associate Director of the Agricultural Autonomy Institute here at Mississippi State University, and I have the distinct privilege of being your moderator that is here purely to introduce the speakers and then quickly exit the stage. So that's exactly the script that I'm going to follow. Would you all please join me in welcoming our first invited speakers for this particular session, Dr. Christopher Hudson and Dr. Marcus McGee, please.
Oh, yeah.
All right. I do now. I don't have anything to fidget with. I got to stand up. All right. Can everybody hear me? All right. I cannot stand still and talk, so I'm going to perform around and talk to you all. Right? So today we're going to talk to you a little bit about from hose to hardware. All right. I am an animal scientist. I am not a computer scientist. Right? So I'm going to kind of focus more on the agricultural side. And my collaborator here, Dr. Hudson, is a computer scientist, and he's going to hit some of the other side of things. And you'll see while we're talking, why we work so well together in this collaboration. But before we start, we need to talk about some of the problems, right? So there are some issues in the livestock sector. One of the things we need to think about is there's a lot of animals per actual producer. Okay? So that means, I'm sorry. So that means that since we have so many animals per producers, right, it creates kind of this labor issue that we have. And with this labor issue, we need a significant workforce, but there's another problem associated with that workforce. We're kind of starting to lose some of this workforce because that generation of producers is getting a little bit older. And generally what happens is that is passed on to the next family member. But as we go further and further out, these new and up-and-coming producers are getting farther and further removed from farming or producing animals, right? So we have a problem. So with this decline in young career seekers, right, we kind of establish this weird paradox where we need to have wholesome animal food products for the future with this increase in population density by 2050. Go ahead. So we need to embrace the future a little bit. So what that means is we need to kind of look at what's forward. And with that being said, there has been an increased interest in precision agriculture. And that's the key word there, precision agriculture, over the last over 20-something years, right? We've kind of seen it a lot. We have major corporations involved in a lot of this. And so we've kind of seen a lot of this, but there still lies a significant gap of application in the livestock sector. All right? We've seen a lot of these sensing technologies applied in the horticulture as well as agronomy sectors, but in agriculture and livestock agriculture, we hadn't seen a lot of it applied. So that creates another thing, right? That creates an opportunity for us. So what that opportunity is, we can apply some of these established methodologies and technologies to the livestock sector that has already been proven inside of the agricultural sector that involves agronomy and horticulture. And on top of that, by doing some of this tech-savvy stuff, we're kind of enticing this new generation of producers that have never been born without use of the internet to actually enjoy the production side of livestock farming. Okay? So we need to move on to autonomous herding and talk about why it's a thing. Okay? Well, when you're moving animals, there's a lot of different things associated with it. Okay? But we need to kind of integrate a lot of these pieces to make it work for the producer as well as the animal. And I'm going to pass off to Dr. Hudson.
Thank you, Marcus. So the question becomes, what components do we actually need to do autonomous herding, right? How do we build out a system that's capable of interacting with animals in the pasture, in the dairy, be able to navigate from point A to point B? It's a lot of the same sensors and equipment that you use when you interact with plants, including GPS, LiDAR, computer vision techniques like YOLO. You've seen probably a lot of presentations of using YOLO to count things. There's a lot of good posters out there and talks that have happened over the last 2 days. And then, of course, we need drone systems, autonomous ground vehicles. These are all different ways that are being explored to herd animals or other types of livestock. Our focus so far is on ground rovers, unmanned ground vehicles to do that. We need to make smart and integrated decisions on where we're going to drive so that we can move this livestock that has feelings and plans of its own that might not always equate to where we want them to go, right? So we have to understand how they're going to move, how we can adjust our movement in order to entice them to go in the directions we want. This has a multitude of problems associated with it, right? We know localization is a big issue. We need to keep track of these cows, in our case, within our global and local space so that when we're trying to navigate to a specific point in order to move them, we don't accidentally hit them, right? So we have to keep track of obstacles, particularly if we're in the freestall environment where it's much more narrow. We have to make real-time decisions about where we are and where we need to go. I have no idea where it went.
Just blank the screen. Computer science.
That's right.
Yeah.
So what's our plan? How are we going to do this, right? Well, we really need to establish what's feasible, what technologies currently exist that we can integrate into our unmanned ground vehicles or our robotic platforms, and what limitations exist when it comes to interacting with livestock in the pasture or in the freestall.
So here's the thing, all right? We know that we can do it. Well, we don't know that, but we assess that we can do this, but at the same time, we need to kind of figure out how to optimally integrate it, right? But there are two big things that we want to focus on, and those two big things are herding or movement of those animals, as well as continuous individualized animal monitoring. And so you might ask yourself why you even worry about the monitoring side of it. Well, producers enjoy getting data, right? But they need data that they can actually utilize. So we have herd level data that works, but it doesn't work well. If we have individualized monitoring, we can actually make some really, nice decisions upon those animals, which way we need to treat them, if we need to cut or cull, and we have more granularity in that herd.
So then the question becomes, what system are we using? Well, we're using the one that's available to us through the Center for Advanced Vehicular Systems. This is a ClearPath Warthog. This is our primary robotic system we've been using in the pasture. It's about a 4 foot by 4 foot by 4 foot cube, essentially, that can go somewhere between 10 and 15 miles per hour. Something I didn't know is cows move pretty quick. That surprised me. If you don't know that. On board, we have the option to operate LiDAR. We have 32 beam and 64 beam Ouster LiDAR. We use RTK-corrected GPS. We have IMUs on board. We have a 16 terabyte network storage, which we can record all that data to. And currently, we have an AGX Pegasus on there from NVIDIA that has about 320 TOPS of GPU power, and we can support up to 16 cameras to do as much monitoring or tracking of cows in the herd as possible. And as a side note, you'll see some videos coming up. This thing is technically amphibious, so it works really well in some of the muddy pastures that you'll see.
And so in this whole scenario, we're aiming towards robotic management. We're really aiming towards autonomy. But before we get to that stage, we need to kind of talk a little bit about animal and robot interaction, right? Because if any of you have ever worked with animals, you know that it's not a static thing, right? It's a little bit unpredictable. And so you have to kind of realize how that animal's going to move, and you have to use some human input, basically, to kind of train towards that. And so we have to use some of the traditional methods, such as looking at flight zone patterns, right? And movement patterns of how to move these animals, and how to catch animals that leave the group that you're actually herding at the time. So you have to use some of those traditional things and train it in. And so you have to look at the livestock's perspective of how they actually respond to the robot, period. All right? So how they respond to its presence, to the noises it's make. Remember, this is kind of a foreign thing to that animal. All right? So the noises it's make, the actual movement, the approach angles, and the absence of human presence is a big thing. Overall, we can move towards designing robots that kind of mimic a more natural or more human handler, right? So it can look like a human, it can move more like a human, so maybe that would actually seem more humanistic to the animal and they can actually respond better. A big aspect of it is ensuring the animal welfare side of it. Now, this thing is going to be on farm, doing its own thing, but at the same time, we cannot forget the human factor. And so we need to make sure that there's no welfare exploits being, targeted during this entire movement event, and make sure that those animals are still handling everything the same way they would as if a human handler was present in that scenario. So that's a big opportunity to make. And so we have to incorporate some of those ethological principles associated with handling in this robotic management style. So from a research standpoint, there's already studies done on some of the stress responses, heart rate, and behavior changes during some robot-led management. And if you look at most of those studies, especially on the dairy side, a lot of that is due to robotic milking, right? It's not actually moving these animals. Now, we know that moving animals automatically kind of increases some of those stress responses, depending on how the movement event takes place. But we need to kind of characterize those and see what actually happens based upon robotic management, because that is a great unknown at this point. And so once we figure that out, we can start to kind of tailor robotic movement towards that to kind of minimize the distress that the animal may undergo during robotic management events overall. And the other side of it is we don't know how animals will react in general, because animals have different personalities. And with those different personalities, we might have some animals that are kind of terrified and some that are really curious, right? And in that case, we have to kind of take into account those types of things as well when we're kind of creating something towards autonomous or robotic management. And another big association with this is, remember, I said it before, we're not removing the human factor. And that's a big component of it when people hear autonomous management or robotic management. We're not removing the human factor. There will always be some component in there that we make the final call.
A big part of how we see these systems are as workforce multipliers. You have a declining workforce in an expanding field that has to continue to grow. How can we integrate these technologies to serve in that workforce multiplication way? So here you can see what it looks like from the robot's perspective, herding cows in the pasture. And then, of course, we have to give special thanks to Raspit that's come out several times and collected aerial footage for us and given us some really nice video shots over the past few years on some of this work. So applications kind of in practice, what are we doing? We're looking at how do we herd. That's not strictly restricted to dairy cattle, right? That's what our current model is. That's what we're currently pursuing. But this can be expanded to sheep. It can go to goats. We're talking about different off-road environments, right? These are not clean, clear-cut places that are always easy to navigate. Yes, they're open fields, but open fields get muddy. If you've ever been out in a pasture, sometimes you can sink past your ankle in mud. You have to have ruggedized vehicles that can operate within these rugged environments. Beyond that, we need to be able to gather animals, sort them for tasks like milking or getting medically checked, as Marcus was mentioning before, cutting that cow or that goat or that sheep out and notifying a veterinarian that there's something wrong with that animal. And then, of course, search and rescue applications. If a cow or livestock is missing, can your robotic platform go and find it? So again, I think that was an autoplay one. We're going to try that again. So this is kind of what it looks like from a 500-foot or 400-foot perspective. Again, thank you to Raspit for this. We were looking at essentially how close do we have to get in order to actually move the cows in pasture. And when I say exclusion zones here, we're actually talking about from the edge of the fence. Could we move them while not getting within 0, 5, 10, 15 feet of the edge of the perimeter to mimic natural barriers such as rivers or streams or lakes that cows might get in? We need to know, can I entice a cow to move from 15 feet away? So,
oh, yes. So this is what I lovingly call our promotional video for this. But in this video, you can actually see exactly what's going on now. Keep in mind, this is human controlled at the moment, working towards autonomy. But this is me actually controlling the warthog and moving the animals using more humanistic patterns. So I kind of go up to them, and you notice I don't have to get all the way in, but I swoop around behind them. And they behave, and they don't run, they don't jerk, jump and run. They actually kind of move along. Now, at the same time, you will see at some point we're going to have one heifer that actually walks off to herself. right? And so there's going to be some learning experience or some training experience there that has to take place to teach an autonomous vehicle to say, hey, let that one go, keep the rest of the herd together, and she will come back, right? Otherwise, it may say, hey, the collection is broken, we need to come back up and start over, and that's not the case when you're actually doing it in person. And so there's a lot of opportunity to kind of train towards all these things, but in our case, as a preliminary study, this worked out really well. And this is the video. It's been posted a lot of different places so everybody can see how it happens. And during this, we collected tons and tons of data, I believe, 5 terabytes of data from 3 15-minute trials. And so there's a lot of data to dig through, and we can still get a lot of things done based on just this preliminary data.
So we've shown you that we can robotically herd them. The question becomes, well, how do we get more value out of that, right? What do we actually need to do from the sensing side? So one of the first things we did was we grabbed a basic YOLO model. We said, well, can we even identify the cows in our camera, right? And this is just showing you an untrained base YOLO V5 pulled straight from GitHub running, and you can see it does a pretty good job identifying the cows. That wasn't really good enough for us. We need to know individual cow IDs. If we want to do that individualized health monitoring, we need to know specifically this is cow 2024, right? Cow 628. A lot of this work has actually been done by Sierra Clayton, who's right there, a master student of Marcus, collecting this data in the free stalls. So we took all of the sensors that we would include on our robotic platform, and we outfitted the free stalls with these cameras, collected data over several trials, and trained a YOLO model to identify the cows based on specific ID from labeled data. We used less than 300 images for this daytime data collection.
Yeah, and the key to this is, like I said, I'm a simple animal scientist, and so I wanted to make this a fairly simple process. So our images are not pre-processed. They're pretty much raw images that we've run through just to see if it will work. And we've actually had pretty good success.
You're not using RFID, you're using actual ear tag numbers?
So as far as actually identifying the animals, she has been actually splitting the frames and actually doing bounding boxes around each animal for the training side. And then we don't have RFID at the moment.
We're identifying patterns on the Holsteins based on their sides.
Yeah. So in the future, I'm probably going to go over time, Madison. I apologize. Okay, we roll. But in the future, we do plan on doing some automated actual collection of data towards identifying animals to place into the algorithm. So running animal single file to capture images and things like that. And so,
Just like this, we were going through these, with this smash tip and
Mhm.
with the bar sensor, and then the treatments like you have, getting that behavioral data is very good for the enrichment.
yeah.
And, because a lot of people say cows don't need enrichment, and they feel you had to brush, and I talked
Yeah.
about it.
Yeah. Yeah. And so that's a extra point there. We can actually see a lot of different effects, and that's what I love about this data is you can analyze it a bunch of different ways, and we can capture a lot of different things. And in this case, we have this individual animal ID in daytime, but in livestock environments, there are lighting changes, right? So you have low light, and you also have night vision. So Sierra's actually been working on that, and we've seen that in low light, we can actually still identify these animals. And so with that being said, we said, well, what about in terms of night vision when the camera actually flips? Well, we actually had a pretty good turnout with that as well. You can see decent precisions overall, and it does depend on number of instances that we actually place into the algorithm, but we're still getting good data with very, very raw data put in, right? And so if we actually go in and start to clean this and kind of make it more producer level in terms of producer ready, then we can actually have some really, really good, hopefully, some really, really good output. But remember, now we're talking about a daylight and a nighttime or low light as well as a night vision model. And so we want to actually take all of that and combine it together to make, the most beneficial and most efficient model for identification. And we found out that in case of low light and night vision, you can combine those models and we still have pretty high precision across the board. Here's just an example of it actually running here. with combined in low light settings overall, as well as combined running in night vision settings, and it's actually giving us fairly good precision across the board in identifying individual animals across the board. And a part of Sierra's work specifically is looking towards estrus detection. And estrus detection is a big deal in the case of dairy industry because you do not get milk without getting a calf, right? You'll get milk, but you won't get a lot. And so with that being said, she's aiming towards detecting estrus using computer vision, and she's using that, and we have it in the daytime, and it's actually been pretty good. So we've used the same methodology in which she's been segmenting those frames and splitting those frames and actually characterizing the behavior based on mounting, right? Go ahead. So we found that in the daytime. So we actually ran that same thing looking at night vision as well as low light, and we found pretty good precision across the board as well with that. So what is this actually saying? That says that computer vision can be beneficial in, one, identifying animals across the board in the varying lighting conditions, as well as identifying the basics of mounting behavior based on animal-on-animal contact. And here it is running on the combined model with night vision and low light here on the right, and you can actually see some mounting behaviors. And there are still some things we can tweak out from it, but remember, this is kind of early stages, and she's a year in working on this, and we're actually digging more through it and finding more opportunity. So with all that, we've actually had some internal funding, and we have a grant we call Making Moves. And with that grant, we're going to kind of do the same thing, looking at behavior responses to robotic management and pasture-housed animals. And in turn, we want to look at some human handling versus robotic handling efficiencies. Also, we want to look at some physiological effects of those animals being moved, as well as some remote sensing for individual health monitoring or early illness detection. On top of that, we've also applied for a NIFA Ideas grant in which we're going to do the same thing, but this time we're going to focus more so on the freestall environment. That's a different environment, more narrow pathways. Our current platform won't work, so we're going to need something a little bit more mobile, a little bit more compact to kind of traverse that alleyway and the inside of the freestall overall. No. And lastly, we talked about kind of integrating this newer generation of tech-savvy producers, right? So we put forth an effort to actually create a course called Precision Animal Management and Animal Dairy Sciences, possibly cross-listening with other departments, that actually kind of train students in precision animal management techniques. So it trains them in the data analysis, it trains them in data science in general, some sensor processing, machine learning, as well as the physiological data collection and how to read those results and actually put forth, a good force effort in terms of illness detection.
So we're kind of running out of time, so we're gonna just jump right to where are we going with this. So we've built out our basic detection model, we've built out our behavior detection model. We're moving towards that data collection that's going to be conducted this summer based on that internal funding, and using that we're going to collect a lot of GPS data on both all of the cows as well as the vehicle, the human herder, and all of the cows, and we're going to build out an agent-based model to look at basically a repulsion factor for where do I need to move to entice the herd as an entity to move based on those flight zones that Marcus was talking about in the beginning. And so initially we're going to do that using GPS tags on everything once we build up that model. And then the natural next step to that is remove the GPS tags from the cows because we want no sensors on the cows, right? You want to be able to deploy a robotic system into its environment to accomplish the task. So once I can do it knowing everyone's position, can I then use LiDAR to localize the herd within my worldview and move it based on where I need to be? Beyond that, Marcus mentioned being in the freestall. We have a confined navigation space. So one of the things we're looking at doing is getting something like a robotic dog, like a Ghost or a Spot, and say, how can we move cows through these narrow freestalls and walkways to the milker and back? How do we raise them from their sand beds so that we can put a thermal on the back of a robotic dog and maybe do a 360-degree inspection, for instance, of the udder?
All right. So I know we threw a lot at you, and I know that it's a lot of applied data that we're trying to do, and I'm showing you our future plans, right? This is kind of a ground-up movement for at least the two of us. But in conclusion, what we like to say is I think throughout careful design right, and implementation, which we're working towards figuring out, that we can actually move towards this and transform the livestock sector with welfare as a main component, right, without kind of removing that human factor. And in doing so, it's not going to be animal scientists, it's not going to be just computer scientists, it's going to be a collaborative effort. And so for all you out there that are thinking about doing something like this, reach out across the board to make sure that you have every avenue covered, because it makes the job a lot easier. Thank you.
Thank you.
Sorry for going over. Oh, no, you guys are good. We're a couple of minutes late getting started. So. All right. Well, thank you very much to Dr. McGee, Dr. Hudson. We sincerely appreciate your presentation. And so with that, we'll quickly move into the next presentation. I do want to apologize. We're going to be a little pressed for time. So questions we'll take if we have the time, and if not, then I'd encourage you to please stick around, approach the speaker after the session is over with, and you can always ask questions then. So please help me welcome our next speaker, Dr. Josh Peoples. Yeah. And then I'm going to help you out with this here. All right, it's all yours, Dr. Peoples.
Thank you, Madison. All right, so I'm from Texas A&M, so we start off with saying howdy. I know we have a couple of Aggies in the crowd, but anyway, so my name is Josh Peoples. Just tell you all a little bit more about myself. Originally from Alabama, went to University of Florida for graduate school, so I know a couple of Gators here as well. And so when I started A&M about 3 years ago, I got recruited for this effort. We're developing this automatic greenhouse data analysis pipeline I'll discuss today. But before we get into that portion, and I'm kind of like the previous speakers, like to walk around a little bit. When we think about plant phenotyping, so phenotyping, just speaking in general, is we have some kind of object of interest, and we want to collect information or trace about this without causing some kind of harm. And so I know I'm talking to a room full of experts that for plant phenotyping, there are a lot of important application consideration of this, right? So, you know, biofuel, food security, different things like this. So the big picture is plant phenotyping is really important. And so with this, the good thing about A&M is that we're a big engineering, big ag school. And so this pipeline has been a great opportunity for us to collaborate on efforts. So echoing what the previous speakers were saying, collaboration is really important. And so just to give you all a big picture, and then throughout this presentation, we're going to walk through module one by one and what we've been developing at A&M. And so starting off on the top part, as y'all know, the most important part is data collection. And so with this facility, we're able to collect high-resolution images of different plants across different multi-spectral bands. We'll discuss in the next slide. After we get the data collected, what our group focuses on is the data pre-processing. Sorry about that. Data pre-processing and analysis. So I'll talk a little bit more about this. And the last one is data discovery. So essentially, we're trying to develop an app that people can use to interact with our pipeline that we're working on. And so the first part, again, most important part is we can't do this work without good quality data. And so if y'all ever have a chance to go to visit A&M, I recommend going to the facility on campus. And so with this facility, we have 2 places where we collect data. And so we have a robotic arm that collects images both at the side and top scan, so we get information across different spatial information as well as across different spectral bands. And so with this data, again, we can analyze it both spatially and spectrally. So if you look at this data, we have 4 different spectral bands, starting with the red edge, red, green, and near infrared is where we can get a lot of information about the plants that we're looking at, and we can extract different indices and different things like this that I'll talk about throughout the talk. And so also part of this, one thing that we're working on is that we want this to be an open source pipeline that anyone can use outside of A&M. And so part of this effort, we've been curating and collecting a data set. So we're going to release a larger one later on, but currently we have this first version. One of my master's students, Jash Amber, who recently graduated, we published a data set over a little over 1,100 images across different crops that we looked at, corn, cotton, and rice. And so for this data set, as a lot of y'all know, a lot of machine learning algorithms are pre-trained on RGB data, so we primarily focus on 3 spectral bands here. And so as with anything, you can add different data augmentation techniques to expand the data set as well. So if you're all interested, the paper's there, and I also have a QR code for those who want to access and use the data set that we have publicly available. Okay. All right, so even with the facility, we collect high quality data, but one thing that we realized that took over about a year and a half for us was once we get this data isn't perfect, so how do you work with this imperfect data? And so just to give you all an example, so when we first started, again, we had these images that we were collecting. One thing that we noticed, if y'all look at the image on the top right, is that we saw like there were these different streaks in the image. There was still this background information from the greenhouse. And so the question is, how do we clean up and process this data so we can actually use it for our algorithms, okay? And so for me, my background is, again, computer vision, machine learning. So we use classic computer vision techniques like connected component analysis, different things like this. But really, we saw a lot more success when we started using different machine learning approaches to try and pre-process and clean the data. And so this is the first iteration of this, and so we made a bit more progress from this point, but just show you all a point here. So given this input image, we have like a two-stage process, and we have like a new pipeline that I can talk about a little bit more later, is that once we had this image, we first detect the plant using what the previous speakers mentioned, YOLO model. And after the YOLO model, we also use a approach published by Meta or Facebook, the segment anything model, to help refine the segmentation process well for the plant. And so I just want to spend some time on this. So this is the focus of my master's student's thesis is, one, how do we improve this pre-processing that I talked about using like these different machine learning techniques? And so YOLO is great, but the baseline YOLO wasn't perfect for our application. And so what he looked at was how can we improve the YOLO algorithm that we have? And so that's where he introduced this spatial transformer network YOLO approach. And so for those who are interested, we talk more offline, but the spatial transformer network is just simply a network that helps add spatial invariance. So it makes your model more robust to these different ways that the plant may appear in the greenhouse, and so that's what my student worked on. And so he took the baseline YOLO model, and at the very beginning, if you all look at the green square, this is where he incorporated this spatial transformer network. And what we saw was both quantitatively and qualitatively, we were able to improve the identification of the plant. So one thing that I've heard across the talks today is that it's really important to establish trust, right, and explainability. And so if y'all look here, here's the input image, right, and we see where the plant is. If we use like this explainable AI technique, so basically if y'all look at this, brighter colors indicate more importance, and then darker colors indicate less importance. So the idea is that we want the model to really pay attention to the area of the plant. And so if you look at the baseline model, it really looks at the area of the pot, which we really don't care too much about. But with the new approach that we introduced, it's able to pay more close attention to the area that we care about. And so this is something that my student showed with his master's thesis for this work. Yep. Yeah, great question. So so the question was, are we doing like a 3D scan? That's future work that we're going to do, and I'm going to talk about in the last slide. Right now, we just have like a side scan and a top scan of the plants that we're working with. Okay. All right. So how many people have taken like a panoramic picture on their phone? Okay. So same thing with the facility, right? And so we're able to take different information of the plant, but it's just still a single plant, right, that we're looking at. So we have to fuse information across different views. And so basically we create a panoramic before we actually process the images within the pipeline. So with this, we do like a simple image stitching algorithms for this. And so say we take 8 looks at the plant, so maybe a very tall plant, right? And so using this, we're able to capture information from multiple different views that we can use for like further processing within our pipeline. Okay. All right, so we got from data collection to pre-processing. Now, how do we actually get insight and more information about this data? And so this gets into the data analysis module that we primarily look at as well. And so we use a package called Plant Computer Vision. I'm sure a lot of people are very familiar with this package. And so we leverage this within our framework to extract different phenotypic traits of interest that people care about, such as like plant height, branching angles, different things like this that we look at, okay? And so from those different characteristics, again, like I mentioned before, we can analyze the morphological traits of the plant, such as the shape, area, height, different things that people care about for end tasks that we're looking at, say like disease detection, okay? And so, we go to someone who's an end user, and I've had this conversation before. Everything I just talked to you all about is measured in pixels, but pixels has no physical meaning to someone, right? And so one thing that our group worked on was, can we take this pixel measurement and convert it to some kind of physical measurement that has some kind of meaning? And so here's an example, getting to your question, is that the plants are placed in the facility, right, so we can take both top scans and side scans, and using information that's specified by the user, say like how many times you want to take an image of the plant, how far the camera is, we can actually take those pixel measurements and convert them to some kind of physical distance here. And so one thing about the facility that's great too is that you can collect different metadata. So if y'all look at the screenshot here at the bottom, sorry about that. It collects information about the type of plant it is, the row, the location of the camera, location of the plant that we use to do like our conversion within the software. So this is very useful for like our end goal that we're looking at. And so from there, again, looking at this example here, so we have plant height, we can measure it in pixels, but we want to actually convert it to some kind of physical measurement. So in this example, we convert it to centimeters that people can actually use to have some kind of meaning. And so primarily what I showed y'all was a lot of morphological shape features, but one thing that we can also do is also look at color information as well as texture information. And so we'll kind of go through those briefly in the next couple of slides. So as y'all know, a lot of us use NDVI, right? And so within the greenhouse, we're able to extract this as well. And so we're able to tell if a plant is healthy or not just using the NDVI. Recently, one of my students, so again, we have 4 spectral bands. And so with that, we're actually able to extract a total of 42 different vegetational indices that we can use across different tasks. And so this is the way that we're utilizing color information. So again, my background is computer vision. So my PhD thesis really focused on texture analysis. So if I were to ask you all to touch the surface of your desk or table right now, what would you say the surface is? Smooth, right? So we inherently know what texture is, but the question is, how do you tell an algorithm what is smooth, what is rough, and different things like this? Same thing with plants. And so if y'all look at here, and another thing is that texture is very scale dependent. So if I look at a very zoomed in area versus a zoomed out, texture information is going to change. And so one thing that we looked at for this was, can we measure and quantify what texture is? And so this is a focus of one of my other master students, was using something called lacunarity. And so lacunarity is a well-known texture measure that basically measures the heterogeneity of like your image that you're looking at. So just to give you all an example, if you see here, we have like a repeated checkerboard pattern. So it's very homogeneous, so it has like a small lacunarity value. But as you transverse towards the right, you get a very dispersed, non-homogeneous texture, and so lacunarity can change. And so we actually use this on plant data, where this work was presented at the Computer Vision and Power Recognition Conference. That's really a top of our field, at the Vision for Agriculture, where we showed that lacunarity can provide more insight looking at these plants in the facility. Okay. All right, and just to wrap up here at the last module, so we did all that work, right? But I give it to the end user, so I really like the previous presentation, the good collaboration. None of these people are really experts with computer engineering, computer science, right? They just want a tool that gives them the answer. And so that's what we're working on for this last module. And so with this, and actually one of my former students in the audience, Uday, was a big help with this, was developing a user-friendly app for us to use for like our pipeline. And so here, everything I just showed you all is just in a one convenient tool that someone can just press a single button and it does everything for them. And so with this tool, again, this can be applied to multiple images, not just one or one plant. And so a user can easily go in and just say, oh, let me look at the height of all the plants I'm looking at. Let me look at the area. And also one thing that was really important was for us to establish trust with the user. And so someone can easily say, oh, let me look at the plant height estimation and let me look and see visually, does the plant appear to be like the tallest plant that I'm looking at? And so there's something that people use to help establish trust here. Okay? Yeah. Was it? Oh, sorry. The question was, is it in the growth chamber? No, it's not in the growth chamber. No. Yeah, great question. And so from there also, again, you can use your favorite tool like sklearn, other deep learning frameworks, because we're able to also save out our information via like an Excel spreadsheet as well that people can use. And so one thing that's important, I think attended one of the sessions today, documentation is really important, right? You want to make sure that people can understand what you're following. And so one thing, again, this is the open source tool that we want to start for A&M, but also open it to other people who may potentially find this useful. And so we also provide documentation to get people started with using our tool as well. So for the theme of this session, this is autonomous systems, right? And so moving towards autonomy, we have all these individual modules that capture things. The next step is how do you synthesize and provide feedback to each module based on the different tasks that you're performing. And so we're currently using Apache Airflow and other tools to try and host and monitor our pipeline just so we can provide feedback to the users. If something fails, we know what fails and how can we fix this for later uses. All right, so just to wrap up here, so I threw a lot at you all, so if you don't remember anything else I said, we have developed like an end-to-end data pipeline that we're able to use going from data collection to pre-processing to analysis to discovery using an app. So like I mentioned before, we're curating a data set that we want to share with the community. If you all go to the QR code link here, this goes to the object detection approach that we introduced, as well as the data set that we shared. And for those who are interested also, this has been featured on different news outlets, so be happy to look at those on our Light website as well. And also we've had the opportunity to present this at a workshop last year. So getting to the question earlier, so actually got some seed funding as well for a new effort too, where we're also looking at doing 3D scene understanding. And so one thing we're working on with the facility is can we collect this information and start doing like 3D plant phenotyping. And so this work was just funded in January, so hopefully for next year I'll have more results to show you all there. Also, as we all know, ChatGPT, LLMs are really big. And so one thing that we're working on is trying to figure out how do we incorporate these foundational models to help us with our plant phenotyping within the facility as well. And so that just to wrap up here, I just want to acknowledge the funding resources. This is AgriLife. Also want to thank the committee I meet with once a month, especially Dr. Murray and Dr. Harden, as well as Troy and Andrew for the management. And of course, I can't do this great work without a great group of students. So I just want to thank my lab members as well. All right. Thank you all for listening.
Thank you very much. All right, so we actually do have time for a couple questions if you're interested. Y'all, in this instance, we do have a couple of minutes for questions if we have any, and I've got a microphone. Okay, so I'm going to come out here.
Okay. Yep.
Thank you. So at what point in time can you tell me in my soybean field how many weeds I've got, other extraneous plants that are out there?
Yeah, that's a great question. So right now we've been mainly focused on the greenhouse, so definitely like a more controlled environment. So to your point, I think the next step is seeing how robust it is to like these non-controlled environments. So this project was funded for an additional 2 years. So I think hopefully like after like next year we'll start trying to see how does it generalize to like other environments. So, yeah.
Any other questions? No? Okay, I checked online on the chat too and did not see any questions on the chat, but we'll use this as a reminder. Anybody that's registered and attending virtually, please, feel free to use that chat feature to be able to submit your questions, and we'll be glad to get to those too if we can. Y'all help me thank Dr. Peoples again. Thank you, sir. Dr. Sharda, if we could, I'm gonna flip-flop the schedule just a second since we're gonna have to do a hardware swap for you. We'll do you last, and Shen, if you're okay, we'll go with you next. So everybody, if you would, please help me welcome our next speaker, Dr. Shen Zhang.
All right, this is a surprise. I was hoping to rest a few more minutes, but as soon as I get done with this, I can, listen to the next presentation more carefully. Good afternoon, everybody. I'm Shane. I'm currently a assistant professor in the Department of Ag and Bioengineering at Mississippi State University. So today I just wanted to talk a little bit about a few projects going on in my lab, and really it's more of a showcase of what we're doing right now in terms of the project. And I've got different things here. For example, I wanted to talk about the sensing, automation, and also AI, which is the focus of this conference, and how we are using this type of technologies for agriculture purposes, right? So I'm going to focus on 4 projects today, but really we have a few more. For example, catfish is one of the Mississippi's first number one fish product here. We're also working with that, but I don't have anything to show with that today. So the 4 project I wanted to briefly talk about in terms of the autonomous agriculture system. The first one is I wanted to talk about the robotic cotton picking project, which is a project funded by the Cotton Incorporated, and also a Kingberry robotic harvesting, which we're currently focusing on the blackberry primarily. And also the rest of the 2 projects are mostly related to the virtual farms. We're developing this type of simulation environment for autonomous agriculture. All right. So this is the first project I wanted to talk about, which actually incorporates a few different steps. So Deva is the PhD student that I have right now who's working on this project. So basically, we developed the system which can automatically go ahead to detect the cotton, do the localization, and go ahead to use the end effector to do the picking. Although we're still working on the preliminary design of the cotton, the end effector, but I will talk about a few other steps. So the first thing I wanted to talk about is the cotton eye perception system that we have. So with this system, sorry about that. I need to back up a little bit. Just give a background information. So cotton obviously is a big deal in the state, in many of the southern states as well. In Mississippi, cotton is the first top 3 crops. And nowadays, we're using these large machines to do the harvesting, and oftentimes it can create some negative footprints on the environment. So the idea is we wanted to create this type of small-scale machine, which can, which will be very light and low cost, and later on we can have multiple agents working at the same time in the field instead of only one giant machine. So this is the kind of the hope that we are having right now. For the perception system that we're working on here, we have developed something called cotton eye perception system. So with this system, we're hoping to do 2 things. The first thing is we wanted to use the perception system to help with the navigation, right? So what we call navigation assistance. Basically, we can use this camera and deploy some of the models, for example, YOLO, which is very popular, and do the scene segmentation of the farm environment, and use that for facilitating the navigation. The second task we're hoping this perception system can do is regarding the detection and localization, right? So we can use this type of perception system to see where the cotton boll is, and we can send the end effector to the targets and do the operation. So in our system, like you can probably see here, we actually have 3 cameras. So the front camera we call primary camera is for navigation assistance, and we have 2 more cameras, one on the left, one on the right, for doing the detection and localization. So after we detect them using the trained model here, we can do a segmentation to see where the exact the seed carton is, and then send the end effector to the exact location. So this is the system actually we put together 2 years ago in 2023. As you can see, this is a robotic platform from ClearPath Robotics, and this is A200 model. And on top of that, we have a few things to make sure the data collection is going well. First of all, we have the 3D LiDAR from Velodyne here, and also we have the front camera, left and right camera. And at the time, we were hoping to collect more data, so we actually added one more camera on the left side. So we eventually end up getting 4 cameras on the vehicle, and we have the GPS. We have 2 onboard computing units here. One of them is a regular computer without GPU capability. The other one is a NVIDIA Jetson AGX Orin. And with all of that, we were collecting data in the Mississippi State University North Farm in 2 of the fields. So one of the fields is this one, as you can see here. This is my USDA collaborator, Dr. Huang's field here. So we collected both before the defoliation and after the defoliation here. And this is the data that we've been collecting. And as you can see, that we have a very diverse data type here. And also one of the camera is a stereo camera, Z2i. So we have 2 views here, and those are from different cameras, making sure that we have a very diverse data set. In terms of the, we know the light condition can create a lot of, impact on the data set. So we made sure that we collect data under different weather conditions. So as you can see, we collected data during sunny days, cloudy days, partially cloudy days, and also even some days a little bit drizzling. So this is the data set that we've been using so far. In terms of the detection and localization task I mentioned earlier, so what we did is we first fit the image. So this is a very typical cotton canopy image, and we deployed the trained YOLO model here. And once we have the detected bounding boxes like here, we wanted to remove some of the, let's say, inaccessible cotton balls there, because they might be in the background. They are probably, fully occluded, and eventually the end effector may not be able to reach it, right? So we wanted to make sure those type of cotton balls are removed. So we added additional constraints here using the confidence level of the bounding boxes and also the pixel numbers on the weight, the height and the width. Make sure that we only get the desired, accessible cotton balls to work with. And after that, we kind of extracted those bounding box coordinates using the center pixels after the detection, and we applied the SAM, so which is also a very popular model called Segment Anything model released by Meta. And with that, we can actually segment out the length, right? So that's the seed carton that we're actually interested in, based on top of the detected bounding boxes. So a little bit roadmap how we end up using this method is we actually first considered just using SAM because it's so convenient. It's label free. We don't have to, get a very student working on the labeling part. But actually, when you look at this, it's not very desired because with or without using the prompt, you can end up getting random cotton balls, and you don't have desired results with all the smaller, very tiny cotton balls in the background and some other things in the image. So we moved on to another strategy using, first of all, YOLO, and then we cropped the bounding boxes out, again, using the detected bounding boxes and the coordinates. But we realized that without the some of the context information, the SAM is not performing as we planned. So we kind of, passed that phase. And later on, we discovered one model called FastSAM. On the GitHub, you will see that they're actually internally using YOLO plus SAM. So they call it the FastSAM. So internally, it will do the detection first, and then do the segmentation after that. We also tried with it, but when we get the prompt, for example, if we wanted to get the 5 number of cotton balls that we want, and you end up getting random cotton balls, right? So you don't always get the desired one that you wanted to work with. So this is kind of the roadmap where we, how we end up using this method eventually. So just a little quick comparison between our method versus the FastSAM here. As you can see, if we wanted to, have, let's say 11 number of cotton balls that we wanted to work with, right? So this is from our model, and if you end up using FastSAM here, you will see that some of the smaller ones in the background are being segmented, so which is kind of not very desired. And we also compared different models, V8, V9, and later on we can extend to V10, V11 as newer models are coming up. So that was regarding the detection and the localization, and we hired undergrad student. Unfortunately, she's just only focusing on the labeling right now. So later on, when we have this type of pixel-wise labels, we can utilize the Cotton Eye Perception System for the navigation. So after we have the perception system, what we're gonna do is we're going to do the actuation, right? So with the target that we already detected, localized, we can actually go ahead to send the end effector or send the robotic arm to approach it. So I know many of you are working with computer vision, machine vision systems, and you will realize that getting a very precise X and Y estimation in terms of the location, that's very easy, right? You can get a pretty accurate result, but in terms of the depths, actually when you have a smaller object, it's very hard to give a very precise estimation in terms of the distance. So that's why we kind of, developed some ways to calibrate the stereo cameras here using the scaling factors, making sure that the camera is working in the optimum range with the optimum estimation on the depth information. So this is the step, and after that we have working on the transformation here, making sure that the different views, for example, when we end up having this canopy image, and the location can be transformed to the camera location, and also later on we can use the location of the robotic arm and even the end effector to automatically reach the cotton ball to do the operation. All right, so after, I think earlier last year, 2024, we finally put together the system. So this is what it looks like right now. It has what we had with the perception system and everything that we had there. And on top of that, we have a robotic arm. So this is from the Universal Robot. And we added the RTK GPS. So this is a Vision RTK GPS K2, so that it can provide very precise localization for the robot in the field. So once we have that, we kind of tried with different ways, trying to make sure that the transformation, the localization is accurate. So we tried with the front camera to control the arm, and also the camera on the left, and also the camera on the right. So once we have that, we are trying to test it in the lab settings. So this is the testing in the lab settings where we utilize the detected, localize the cut and bowl location, and communicate with the arm and sending the arm to the final location. So if you're working in the actual cotton farm, you realize that you don't want to pass the single row multiple times, right? So because you have the cotton plants on your left and on the right. So this is where we kind of combine the control for the arm on the left operation and on the right operation together. So this is the kind of a demonstration in the lab situation where we have the arm moving on the left, on the right in the sequence, and we have a Python script to determine where the arm is currently at, and once all the detected cotton bolts are finished, and it will move to the next. And the hope is later on, when we move to the field, we can continuously let the vehicle to move forward and keep harvesting on the left and right side. So this is a little bit demonstration from last year in the field. And thanks to the diverse data set that we've been collected under different weather conditions, and it was actually working very well without any sort of background, black background or any artificial lighting system. So the system worked pretty well in terms of the detection localization. So moving forward, so a little bit statistics in terms of the field testing last year. As you can see here, we have developed a few matrix to evaluate the system in the field conditions, right? So if you look at the processed cotton bolts, this is really where we utilize the perception system to filter out the undesired targets and only focusing on the ones that are reachable within the working space. And a few other matrix: successful penetration, successful exit, reachability, and correct positioning. I didn't do a math here to show the percentage, but as you can see here, we have achieved most of the cotton bolts right here. So at the beginning, we had some kind of arrows here with the NaN value, which basically is the perception system telling us that the detected cotton bolts is not, we cannot send the any factor to there. So later on, we utilize the joint control to avoid those sort of arrows. And moving forward, the second, I think I need to maybe move a little bit quickly. The second project I wanted to talk about is a collaborative efforts that I've been working with Georgia Tech, and the project is regarding the robotic kingberry harvesting, and currently we're working on the blackberry harvesting. So I've been working with Dr. Chen and Dr. Zhao from Georgia Tech, whose focuses are on the soft robotic arm and also the bipedal locomotion here. So our focus here is to develop a very high accuracy, precise computer vision system or perception system, I would say here. So as you can see here, that there are a lot of challenges when you deal with the kingberries, right? So if you look at the skin of the berry, it's very delicate. It has different droplets, and also another important thing is this type of berries are really small. So when you look at it, it's only a few, maybe centimeter. So it's really definitely a big challenge for the perception system to accurately detect it and localize it in the 3D workspace. So currently, if you look at the BlackBerry harvesting is mainly manual, so people are harvesting them manually. So we just had a PhD student joined the lab in January. Jonathan is working on this, so not much progress to show, but I wanted to maybe give some of the preliminary results. We started with the detection, very simple work, right? So we kind of identified 3 different stages, classes of the blackberries. So the first one is ripe, and we're looking at the blackberries is mostly black or dark purple, and also in the second stage ripening, where you can see those pinkish or more red color of the blackberries, and also if you visit the field, you will see a lot of the unripe berries are, they all show up in the same canopy at the same time. So basically, the job for the first step for us is to kind of identify different classes of this type of blackberries, right? So this is the YOLO model we've been working on. We tried different versions from V5 to V8, and we stopped on that because we know that with newer and the more advanced model coming up, we can actually do a better job. So this is the detection part. In terms of the very, very preliminary field test. So this is the initial field testing we did together in Georgia in 2022. So this is the robotic arm here. This is a software robotic arm Dr. Chen's lab is working on. And we tested our preliminary computer vision system, perception system there using a Z2 camera. So a few things or a few, issues we noticed at the time is, as I mentioned, this type of berries, blackberries, are really small. So if it really gave us a hard time to estimate the distance in terms of where the actuator is, and also the berry is on the canopy. So the second thing we noticed here is what we trained in the data set is we trained the images without any of the interruption of the arm, right? So, but in the field testing, the arm is moving and the arm is entering the frame. At the same time, the focus of the camera may change, and in that case, the background got blurry, and the detection accuracy quickly dropped, and that really gave us some hard time. So we're still working on this, but I wanted to show you this. And for us, since the blackberries are really small, so we really wanted to utilize a good camera with higher accuracy to do the estimation for the distance. So this is actually on the right side. We have a IDS camera, which is a fairly expensive camera. I think it costs around $10,000 for that camera. But when we test the different smaller objects, and it really gave us a few millimeter of errors in terms of the depth estimation. So this is ongoing work. We're going to investigate how well or not very well of this camera for this specific task. All right, switching gears a little bit. Do we still have time, Madison? Okay. I'm going to really, just move a little bit quickly here. 2 efforts are going on regarding developing the simulation work. The first one is we're trying to develop a ROS gazebo-based simulation environment for testing different autonomous algorithms. So this is the work that Deva is working on. So we recently just finished a paper on that. So this is the virtual cotton farm we developed in Gazebo, And as you can see, we kind of put together the system mimicking the real system that we had in the reality, and using that to do the autonomous navigation. So we kind of annotate the cotton plans that we had there for detection, for segmentation. So really, what you can see here is the work that I just talked about regarding the cotton eye perception system. As the vehicle is moving forward, we can do the detection on the go, and we can do the segmentation on the go. Basically, this is the visual-based navigation assistance, where we kind of utilize the different layers, including the sky, the ground, and also the cotton plants here as the navigation cue. We investigated two methods. So one is GPS plus visual-based navigation. The other one is we utilize a pre-generated map-based navigation for this task. And this is the final trajectory. If you look at these two different navigation methods. So the bottom line is we realize that if you're utilizing GPS plus the visual-based navigation assistance, it's a little bit more efficient in terms of comparing to the map-based navigation methods. And very quickly, just wanted to touch on the other simulation work we've been working on. Actually, Kodai and also Presto, my students are working on them. Kodai gave a presentation this morning regarding it. Mississippi MSU has a very great simulator. It's called MAVS. So basically, it's MSU Autonomous Vehicle Simulator. So they already developed this. So this is the image provided by the developer, Dr. Chris Gooding from CAVS. And what they're doing is they have this type of simulation, and they provide different terrain, different vegetation for primarily testing just some military-based vehicles. But what we wanted to do is we wanted to create this agriculture environment for us to test the agriculture autonomous vehicles, right? Not only the military vehicles. So that's why I give the name. It's called AgMavs here. So really, we're working on top of what they have already. So they have, this is the slide I stole from my students. So they have different sensor simulation, for example, RGB cameras, depth cameras, and also LiDAR sensor here, and it can also simulate the RTK GPS. And in order to create the simulation, we need to have the agriculture environment, right? So this is basically last year where we just started this project. We brought the cotton plants from the field in the pod. So we brought back the potted cotton plants and do the background removal using SAM and do some structure from motion. And as you can see here, we kind of just reconstructed the 3D cotton plant here. And eventually, when we have the meshes, we can convert that into the object, into the OBJ files there, object file, and import it into MAVS environment. So we end up having this is a cotton field, so where we can test the different things. Very quickly, these are the 3D reconstructions that we have currently. So the last one is I've seen a few different studies on that using 3D Gaussian splatting. And we also collected different data in the field in order to check whether the simulation is realistic enough or not. So if you really compare these two sets on the top row, this is actually the synthetic images we end up having right now in the AgMavs. At different time, you can change the location as you wish. And on the second row here is the real images we collected from the AAI's field last year. And change the, like I mentioned, change the terrain type, change location, and here you can change the weather, you can change the cloud cover, etc., to mimic different, scenarios to close the try to close the gap. So this is the last slides that we'll talk about. So since we kind of collected 3D meshes in the lab last year, which is really time consuming and not very convenient, so this year we're going to utilize the Amiga platform, and we're going to collect the 3D meshes in the field as we go using the platform on different crops. So we're going to extend it to corn, early stage corn, and also soybean that will be planted in the AIS field. And with that, I just wanted to maybe highlight quickly on my research lab, great students I'm working with, and I'm also co-supervising some of them with my colleague. This is the funding support, and thank you for your time. That's the last slide. Thank you.
Thank you so much, Dr. Zhang. And no time for, well, I'm thinking
I'm sorry.
I'm talking into a microphone when I'm not. So no time for questions, unfortunately, but Dr. Zhang will be around, and so if you have questions, please seek her out at the end of the session. We've got one more speaker, and if y'all will bear with us just a moment, we're going to do a quick hardware swap from this laptop over to another machine. Thank you. All right. All right, so let's do that. All right, thank you so much for your patience. So everybody, if you would, we've got one more speaker. Would you please help me welcome Dr. Ajay Sharda?
Thank you, Madison. And thank you, everyone, for being here. I won't take too much of your time between now and dinner and everything what is planned in the football stadium. So like Madison said, I'm Ajay Sharda. I'm a professor in the biological and agricultural engineering at Kansas State University. I'm also representing the Institute for Digital Ag and Advanced Analytics. It's a pretty fairly new institute at the university level. It is directly under the Office of President. But it's a bigger initiative where we are really bringing the faculty from multiple disciplines. We heard numerous speakers in the industry panel this morning that how interdisciplinary teams are needed to really solve the problems what we are facing. We heard from the CAVS lab and Dr. Peebles, so it's very relevant from that part. One of the other focus from the ID3 standpoint from us is that we really want to bring in larger faculty from different departments into the fold so that we can connect them with the people who have other expertise beyond their focus area so that they can make these projects a little bit more holistic rather than focusing on what they are really good at. We have a focus at the school level that they want to encourage younger faculty and everybody else to go for startups, entrepreneurship, and really look for larger funding for strategic industry engagement. So I think that is going to be a focal point in terms of what we do from here on. So just moving forward, what I am going to talk, so we have seen a lot of things from phenotyping and a lot of specialty crops and everything. I'm going to focus a little bit more on the row crop production side of it. And what we are looking at from what's happening in the technology development phase is we've seen equipment which has gone bigger and larger, more speed. We have continued to see more action in terms of vision-based things. we collect a lot of data. We heard from the industry panel as well that we have a lot of data streams coming in, but how easily can we get that data into form of some sort of a knowledge is still being a challenge, right? We talk about precision ag, we talk about digital ag. We were looking at how we can harness the data and get it back into the use case scenarios. So if we look at the large machines, I'm really going to focus on planters, air seeders, sprayers, and all that stuff. We have seen a lot of things in terms of high resolution control and feedback, which you have seen in times to come. We have seen boom controls and see and spray aspect of it. You might have seen something which is going on the seeder side and planters, whether it is the furrow vision and all that part. But then in advancement to that as well is the embedded intelligence into the machines as well, right? One thing which we have seen in the recent past, in the recent time, is that we have been collecting lots of data, right? And we have continued to grow in terms of what is visible on the screen. What is more important from a farmer's perspective as well is that what can the farmer use while in the cab, which is meaningful for him or her to make decisions on the go, right? That's something is of our focus, that what can we bring in terms of data. I know people use planters here, and we've seen some sort of a downforce systems on planters, which are fairly common these days. But a lot of these things are still pretty intuitive in terms of people have to go and do hit and trial thing, and you're going through your field. You have to do a lot of selections in terms of what you do. But I think some of the things which we can do with data, which we collect a lot of data on these machines, is to use that data on the back end. Whatever we can use deep learning methods, we can use machine learning models and all that stuff. And those data sets should be able to help the farmers to make decisions on machine control without the operator making all these efforts to do that, right? So that is where some of the things which we talk about, the autonomy in machine control, and the visualization is coming in. You've heard a lot about autonomy, a lot about automation aspect of it. We saw bigger, tractors. We saw smaller tractors, right? But I think what we all seeing is that there is definitely a pathway and a road to autonomy in terms of what people want to see, right? So from a current innovation standpoint, we are all putting some pieces together so that at one given time we can make these machines run by themselves. So with this kind of a little background, in place, I put few slides in there, and we were talking within our team and talking, we are here at the AI in Ag conference. We were all talking about why. That has changed significantly in the past many years, right? So these things have become more accurate, more fast. Think about how using these things to develop solutions. That was probably not a possibility or a success story a few years ago. The other thing is the aspect of edge computing. I don't know how many people are training large models, using lots of data in terms of image things and what kind of systems you need. We have lots of tools available from a cloud standpoint where we can train models, we can annotate things, and that has really hastened the process of what we want to do from large-scale data processing and model building aspect of it. And I think the thing which is really driving the AI and the use of AI in our aspect is the cost, the efficiency, and the profitability part of it, which can come in terms of these AI-powered things. Well, when we talk about all these things in the row crop production, we have 24 row planters. We have even wider planters to talk about. We have large air seeders, and when farmers are going across the field trying to plant couple of 100,000 acres or 20, 30, 40,000 acres in a small window time, 20 days, 25 days. There's a lot going on in the machine aspect of it, right? They can do few things, but there are a lot of things which are just not possible to do from that standpoint. When we talk to farmers that, have you seen this technology, or what would you like to do from an AI standpoint? Obviously, things come out with, in terms of trust, like how good that is, how can you show me the value of all that part, how much it costs, what will be the upgrade scenario on that, what kind of serviceability is available, how easy for me to use it, how often I have to replace that part. But among all that part, they are still very cognizant about what these technologies can bring in terms of value proposition, right? I don't know how much people are aware about where the cost of a seed of a bag is going, or the chemical cost is, going up in terms of, what you want to do. But I think the ability of these systems to precisely, apply things and have some precision, that's one of the things which is of a biggest value. And obviously, between Craig and Andrew Oliver, I think the profitability aspect of it, the ROI, I think you have started to hear more and more about what's the return on investment on if I put value, my investment in this kind of a technology. How much productivity gains I'm going to have. We did not have these questions too often earlier, right? I think we have been adding a lot of technology in the past many years, but how do we show the value in terms of what this system is doing for you? That has really gained some focus. So what I'm going to do is I'm going to really talk a little bit about, so when we talk about large machine systems, especially planters and all that, what our focus has been in the last few years, we're trying to build systems which can gather data, which is very specific for optimizing the machine operation for the farmer, right? Let's just take an example of seeding operation when we are putting seed in the ground. While I'm doing the seeding operation, once the seed goes through the seed tube and the trench closes, I have very little opportunity to know where the seed was placed, how much trash was in the soil, whether the seed was placed in the center of the trench or it was lodged in the side of the trench, right? How does the closure happen? What was the surface finish of the thing? So there are a lot of things which are happening so fast. The other thing which we have to be cognizant about, if we want to put something like that on a machine, it better be working during the planting operation, right? If you have been out in the field doing these things, you have lots of crop residue and dust and everything which is flowing by. And more importantly, when we are trying to put these systems on these machine systems, we have a very, very small, footprint available. Not only to put these systems, but also we have a very small window to look at it. There are a lot of things, right? If you see modern days row unit, we have row cleaners, we have opening this, we have smart farmers, we want to put, AccuShot thing, we want to put some, furrow vision aspect, we have press wheels, we have closing systems, if you put all these things together and you still want to see something, that's the challenge, right? So I really want to bring the focus, when we are trying to, build systems around these machines for a real world operation, things like this, variable environment and, complexity of weeds and soil. But I think one of the biggest thing is the computational requirement for real-time operation that comes in. I think the integration with the existing systems, how do you take the feedback from a vision system and take it to the cab to make sure you can make some changes in the machine while the operator is doing his job, right? Or her job. The second, another thing which is really, really important for us is the robustness and the reliability of the system, right? When you put that system on the planter or a sprayer and you expect that to work, 8 hours, 10 hours in the dust, all the weather conditions. During transportation, it should not break. Those things become very important as well. And obviously, we're talking about maintenance and calibration and upgrades of all that part. So what I'm going to do is I'm going to share a couple of examples from what we have been doing in the past. If we look at the seeding operation, we used to do a lot of work on farm, and some of the grad students used to go out and dig out 4, 5, 6,000 seeds every year, and this happens around the summer period in the June. And I think if anybody has gone out and dug seed, I think this is one of the most painful jobs to do that, and I think that is what is stemming out from the need aspect of it. So the long hours and all that part. So this is one system which I think when it seemed like we have seen the Furrow Vision. I think when Furrow Vision was coming along from a deer standpoint, we were developing a similar system on an academic scale as well. So we have a patent on this system. What this has, it has a camera there. It has a laser line scanner which can give you the depth of the furrow. And then what you really want to see is that as things are moving along, that you should be able to really see what's in the trench, right? I think when you see some things, at a realistic speed, 4, 5, 6 miles, 7 miles per hour, the information which you can gain from a visualization of these kind of a thing is second to none. And I think as soon as you start to see what happens, in the furrow while, when we were putting seeds in there, it's amazing, right? This is a very, very smartly selected video for you because nicely moist soil and very little crop residue, right? But if you see what are some of the realistic situations in the field, this is another realistic situation, like 8 miles per hour, and you are planting a seed in there, all sorts of crop residue and dust flowing in. So what we need to do is we need to make systems which are robust enough and which can be operational in an environment like that, right? So even in these conditions, we can see almost 90+% of seeds, but I don't think 90+% cut out for the customer to use at the end of the day, right? So there are a lot of things to do from that standpoint. The other thing I want to share, when we talk about putting the seed, the trench quality becomes a very important issue, right? So how good the trench was formed, how much crop residue was there, what is the effect of crop residue on the closing system, how good the emergence will be, will I have any effect on overall yield? Does it impact or does it not impact? I think this was also the need in terms of what we can do to learn how good our cleaning systems are, like row cleaners which clean up the way before I open up the trench. And I think it has another importance in terms of what can we do to redesign, to really make our machine systems better from that standpoint. So I'm gonna what I'm gonna show is say a lot of things which are happening in the back end. So I saw some of the visualization from Dr. Peoples here. So this is another example of what you can do here. So basically, if you really want to learn anything about it, the whole story started that when we started working on this, the engineering team, there was a lot of back and forth in terms of what you would like to see. People say that I just want to see only the trench in terms of how good the trench is. Some people say I want to see a couple of inches around the trench, right? So one of the things we did in this process is that we gave the choice to the engineer on the team they want to do work with. They can select the kind of area of interest they would like to analyze data on, and that is how it will do to go out and do stuff. So these are some of the visualization. This is what is happening on the back end, but this is something which the things can see on the back end. You can put the same visualization on the cab so the operator can see it. And at the same time, you can start to make decisions on what kind of machine systems work for you or what changes you need to make from that standpoint. One of the things which is of also importance is that when you start to go in and collect large-scale data sets, and I really appreciate what Dr. Peoples showed here in his presentation, is that it is very difficult to see what happened in the different portions of the field, right? So this kind of a toolbox, really gives access to the people that I can selectively go into, the areas of the field which I think may have had more residue versus less residue. I can analyze data better. I can really start to put, what are the, false positive, false negatives and all that stuff and start to make things, much better going forward. The the another example, when we look at the from a planter standpoint, these toolbars, the planter sizes are becoming larger and larger, right? And when you plant on different terrains, when you plant on different kind of field shapes and sizes, we do not know how much the toolbar flex, right? And when these toolbars flexes, they have some impact on how does the seeding operation happens and where the seed gets placed and all that stuff. So this was just a very quick and dirty thing in terms of what we wanted to learn, but the idea was, can we put something on the planter for a true operation in the field, and what can we learn in terms of how much they flex? So I think some of these examples have really given us an opportunity to learn, which we did not learn, did not know at all before. We thought that the planter toolbar may flex a couple of inches, right? But knowing that this toolbar can flex 6, 8, 10, 12, 15 inches, that gives us a lot of information in the beginning to see, hey, there is something more to learn about, what is going on. On these similar lines, we work a lot with the crop protection technologies. And I think people who have been following some of the crop protection on the large, machine standpoint, there's a lot which has happened from control system standpoint, right? What these systems do in terms of product delivery, product metering aspect of it. But these large booms, whether they are carbon fiber or any kind of, they're getting bigger and bigger, right? We have 120, 135-foot booms, and I think they are going to even go bigger. I thought that's the biggest we can go, right? And then during the operation, from a sprayer standpoint as well, our typical operating speeds are anywhere between 14, 15, 16 miles per hour, and we have all sorts of field terrains. So there's a lot of new technologies which are coming in terms of, boom control aspect as well, but we really do not know how much booms move and what is the impact of that boom movement on the efficacy of product delivery and coverage and the control of weeds from that standpoint. So the goal was to build something which can measure the boom movement both from a fore and aft and vertical standpoint, and then building a model where we understand that what's the effect of boom motion on the product deposition aspect of it. If you guys have seen some of the spray table in terms of how we look at the coverage and overlaps, most of the spray tables with all the manufacturers who are making nozzles and everything else, they just do nozzle calibration aspect. They do not take care of what the boom orientation, because the booms move at a pivot point, right? And as the boom moves at pivot point, the nozzle orientation changes as well. Now I'm not putting the product straight down, I'm putting the product at an angle. And you combine that with wind speed, you combine that with the air streams which are being created by the sprayer itself, we can lose a lot of product in terms of where the deposition is going. So this is another visualization tool in terms of how much the boom is moving, on a vertical scale, and you can do on a horizontal scale as well. But the overall idea is to take this information, combine that with the model in terms of coverage loss, and to really understand the impact of the boom movements on the coverage and the deposition of the product part. And primarily to really drive, what kind of innovations we need to make these booms more stable going forward. The last thing I would like to share, we just finished an NSF-NRI project. The idea in this was to develop a robotic, platform which can go in the rows, mostly for row crops. This is an example for sorghum, and we are doing something to get that same thing in corn as well. So this is the idea in this project was that it should be able to go in the crop. It should be able to see. The aphids was our use case scenario. Yes, those are very small, but also yes, they don't continue to move. We can come locate where those are, and we can spray them, and then we can look at the efficacy of it. So from this standpoint, we were able to really develop complete end-to-end solution. it goes through the crops, it looks at if it sprays, and then it collects all the data, it puts the data on the edge. It has a continuous radio communication system and all that part. But the thing which I'm most excited about going forward is these kind of systems for under canopy navigation aspect of it. So Rahul Harshai is one of our PhD student. He's developing some of these algorithms. And I was coming here. I said like, so how good this is? I said like, I don't know. It's beating all the things which are already existing in the academic field. Whatever is available. So I captured this video last season. We were going across the cornrows, and this it hasn't seen anything. So this was a little video, me walking, taking the picture, and I saw like, let's put that and see how good that is. So this is a generalization of that part. The problem in terms of navigation under canopy is one, it is a GPS denied environment. Two, when you are doing something which is in season, whatever you want to manage, there's a lot of occlusion and noise in terms of what you see, whether they are leaves or plants which are not, straight erect and all that stuff. So that really creates a very noisy environment for those things to navigate by themselves. So we're really excited about really putting this system out in the field this summer, spring, and see where it goes from what we are doing. So in closing, some of the things where we really are focusing what we want to do. I think one of the biggest thing we want to focus on is the quality of job done, right? We have been putting a lot of things in terms of technology, whether it is a sprayer, whether it is a planter, air seeders, and all that stuff. How good that machine was in terms of its intended operation, right? We collect data, it's all digital, but I think to put a value in terms of how good of a job that system has done is still kind of is a question people want to have answers on. So that is exactly what some of the things we have shown from what you're looking at. User access to the knowledge where user can implement certain things. So, taking all the things we are, collecting. I think we're collecting a lot more data which we need right now, but we can very intelligently use some of the existing data sets to generate very meaningful information for the operator in the cab, so those people can make some decisions on the go, right? What's the value of that knowledge that I missed 6 rows or 5 acres here and there to plant versus at the time of operation? I can make small adjustments, whether it is seed tube is blocked or something is not working, versus going back and finding those 10 rows or 20 rows or 50 rows and planting those again, right? That's just not a meaningful thing to do. So that's one thing. Automation of control in terms of complex operations. I think that's what the example I showed or shared with from a planner standpoint. There are lots of machine settings, even in this time and age as well, which are user intuitive, right? There is no set pathway that I can set it, and it can automate that process. We can take an example of, planter downforce, and we can take an example of many other things, right? I set one thing, and as the operator is going through the field, he or she continues to make changes based on what the data is flowing. Do you really think that operator can look at that data and make some sense of it and really make an informed decision? I really don't think so, right? But there we can put very smart engines on the back end and just give a cue to the operator, or actually just do things completely on the back end. So based on all that part, efficient machine control, input use optimization with the cost part of it, that's where it is going. The other thing, the last thing I want to hit from a talking point standpoint, the ease of use part, right? That's another thing which hit in the industry panel discussion as well, that we really need to make these systems which are easy to implement. How can I integrate these systems on my existing machines without making much changes in terms of what I already have on my machine, right? And then on top of it, that they are able to really run and provide me the output I am looking at. So that's all I have to share with you guys. Happy to answer any questions, and thanks for having me here.
All right, so I think we're all out of time, unfortunately, but Dr. Shorter will be around to be able to take questions afterwards. Thank you all so much for your time here. Please help me give one more hand for our speakers.